So welcome back. Today we're very happy to have Nima Lashkari from Purdue to tell us about RG flows as a quantum error correcting code. And yeah, if you have questions, just let us know and we'll bring the microphone to you.
Thanks so much, Brian, and thanks for the opportunity to speak here. So today I'll be talking about renormalization group and error correct RG flow renormalization group as a quantum error correction code. So every time I write QEC, I mean quantum error correction. It's just I don't want to write this over and over again. I'll try to be the discussion. Hopefully, I'll try to keep this as informal as possible. The details are in the papers, so feel free to stop me and ask questions if something is unclear. So every time I've given a version of this talk, I always run out of time before getting to holography. So today I'm doing the opposite. I'll start with holography, and gradually we'll go back and talk about the field theory side of it. So the transition to field theory, you might find it to be a little bit formal, but I'll try to make it as smooth as I can. All right. So the summary of what I'm going to say is this. Renormalization group flow is an approximate, this is important, quantum error correction code in which the logical states are the infrared states, that they belong to some sort of infrared Hilbert space. There is an encoding in every quantum error correction code, which is an isometric map, an isometry, W, from HIR to HUV, so that's the direction. Just to remind you what I mean by this is the meaning of isometry. W dagger, W is identity. And then every quantum error correction code also has physical states, and the physical states are the UV states that belong to some HUV. So what is the error model? The errors are going to be local. This is also going to be important. UV operators. So this is the main structure, and we'll go over this step by step. But given the audience, I'll try to motivate this from holography, or using the language of holography first, and then perhaps at the end we get to the specific examples from quantum field theory. Okay, so some references, because I might not have time to go over the details of the calculations, but you can find all of that here. So the general formalism of quantum error correction code is usually formulated for qubits and finite quantum systems, but it could be easily generalized to any quantum system, infinite dimensional or not. Or said differently, it could be generalized to von Neumann algebras. So this was known to mathematical physicists from the 80s, from the work of Petz. Perhaps not in this form, but we sort of clarified the connection in a paper. Let me just write, I'll skip the name of the authors. In this paper, I'm missing 001. And then everything we'll go over for specific examples of this story. You can look at these papers. So we worked out an example of a continuum renormalization group for continuous quantum field theories, Poincare invariant quantum field theories, formulated in terms of continuous mirror. This was in this paper, 5099. And then, perhaps more familiar to high energy theorists, we're working on, this is some work in progress, the RG flow of ON model, large N ON model in the language of Polchinski's exact RG could also be written as a quantum error correction code, and this will come out soon. So, all right. These are references, so I'll just good. So some key observations which are going to be important are going to be these statements. So first of all, renormalization group could be classical or quantum, and the correspondence to quantum error correction code goes through classical or quantum. So classical quantum renormalization group corresponds to an approximate classical error correction code, and the same for quantum. So it could be classical or quantum. We'll work out an example of a classical error correction code in the C-Mera paper. Second is the error correction is passive. So I will probably, once we get there, I'll explain. But what it means that, what I mean by passive error correction, it means is that there's no need for recovery map. These are simple examples of error correction codes. All right. Now that I'm actually going over this, let me just also tell you about lessons that we're going to extract for holography. So you probably know already that there's a connection between holography and RG flow, and we usually say in rough terms that the radial direction or the emergent direction in holography is like the RG scale. So this, what I'm going to go over, could be understood as a generalization of quantum error correction code in holography to any RG flow that clarifies the role of large N and the large gap. What comes out of it, the thing that I'll try to advocate as the main, perhaps, message I'm trying to send across, is that there are two distinct types of error correction at work in holography. So this is something that confused me for a while, but hopefully I'll try to clarify it now. So the first one, so let me just make a table. There is an error model, mechanism, and type. So in holography, there is error correction that provides protection against heavy UV operators. And the mechanism for that is the large gap in the spectrum of conformal primaries. We'll see that. And the error correction that you get out of it is passive. This is the one that generalizes to any RG flow. So any RG flow with a gap will be an approximate error correction code. When the gap is large, your approximation becomes better and better. The second one is the one that provides protection against light UV operators. The mechanism for this is large N, and this is an active error correction code. So I'll try to clarify this. Are there any questions so far about the plan of the talk? So I'm just going over the plan. Okay, so before I get into the details of this, I just want to clarify this table a little bit more, just in case you lose your motivation to follow the talk once we get to the mathematical statements. Let me clarify what I mean by this. So this is a picture I'm going to draw that is perhaps helpful to have in mind every time we go through these discussions. So let me just remind you what quantum error correction in holography is. And I have to apologize, I might not actually mention. So a lot of people have contributed to this discussion of quantum error correction in holography. I'll try to remember to cite people whenever I remember. But of course, this is like I'm reviewing a lot of work done by brilliant physicists, some of whom are here. Okay, so quantum error correction code in holography. This is a geometry. There is a boundary region A. There is an RT surface that I'm going to denote by gamma of A. This is the RT surface, Ryo-Takayanagi surface. If some of these notions are unfamiliar, please let me know. Then errors occur here. So these are errors. So when I say UV operators, I mean errors are here on the boundary. And the encoded information is out here. This is the infrared, right? Some local operator inserted deep in the bulk and outside of the RT surface of corresponding to A. Okay. So a geometry like this does not represent a single state, but it rather represents a subspace of infrared states, IR states. So I'm using the term subspace loosely, but you'll see in what approximations these become exact. That are all described by the same geometry. And this subspace corresponds to this subspace some projection operator that I'm going to write as WW dagger. This W is the isometry we're talking about. And well, what I mean by this is that if there's a geometry that is described by this state psi, and I act with some sort of a UV operator and then project further using this projection, I basically get psi back. These are stringy modes. These are very, very stringy modes. Actually, maybe I should write it here. Let me erase this. Use this space a little bit better. So I'll make a distinction between heavy stringy modes and the light supergravity modes. So what is the distinction? The distinction is that, let's say there's a point Y that belongs to A. So an operator, I call it heavy, a heavy error, if when you take this operator here and you want to compare it to phi of x, there is an isometry W that brings you here. So if you want to pull this up to compare them, you have to sandwich it with WW dagger. This is the renormalization of an operator that pushes it into the bulk. The W map that we've been talking about is the map that maps the infrared states to the UV states, right? So HIR to HUV. This is this map. So for heavy stringy modes, when you project to the subspace of states that are described by the same geometry, basically the norm of this heavy stringy operator goes away. Meaning that if you were to calculate the correlators between this operator and phi of x and project to the code subspace, not only the commutator would vanish, but also the correlator would vanish. So if you remember, the original argument for holography, for quantum error correction in holography was that operators here and operators here commute, right? UV operators and infrared operators commute. But that could happen in two different ways. They could commute while the correlators are non-zero, or they could commute because this operator, they just have vanishing correlation functions. So in this case, both the correlation functions and the commutators vanish. This is as opposed to the supergravity modes, where the correlation functions don't vanish. So if I take phi of y in A, w dagger, which we usually trivialize this map in our mind, this is not 0. However, the commutator of these two guys is 0. So they approximately commute. So the commutator vanishes. The mechanism, so when we say that in holography we have quantum error correction, for erasure of region A, we mean that we could protect against heavy modes and the light modes. We'll see that the mechanism that provides protection against the heavy modes exists in any quantum field theory, in any RG flow. However, this has to do with large N. These are two distinct mechanisms. And by passive, here, when I say that the mechanism for this, the first one is passive, it's simple because the error in the infrared doesn't act. It just goes away. Whereas here, the error acts and needs to be corrected. But it's correctable. The correctability has to do with the fact that the commutator vanishes. All right. Okay, any questions about this? So this was holography. Perhaps, in part, hopefully, it was familiar. Now, what I'm going to draw on this board next to this is the structure of error correction for a general RG flow. But I'll use pictures that resemble this. Hopefully, I'll have to use color chalk. Hopefully, I'll do a good job. So to simplify our life, let's consider a CFT, right? So we're going to consider RG flow in a CFT. So the first thing you might say is that, oh, RG flow of a CFT is trivial. But that's not true, because we're considering RG flow for a subspace of excited states. Of course, the vacuum is invariant, but excited states run, and the RG flow of a subspace of excited states is non-trivial. So to make our lives easier, we consider a CFT. And I'm going to draw this picture, IRUV, to have in mind. Again, this is an analogy, right? So there is no geometry here. But if you want to think of a geometry, as Brian taught us, you could think of MERA, or a continuous version thereof. So here is the UV state. Here is the infrared state. There are isometries that take you between different scales. These isometries are the isometries of, for example, MERA, right? The unitaries, disentanglers, and the coarse graining isometries. Both of them are isometries. So here's the region A. What happens is that, as opposed to here, where there was a sharp RT surface, where if the operator was inside, the commutator would be non-zero, but then there's a transition, and immediately as you push it outside of the RT surface, the commutator drops to 0 in both cases. Here, what you end up with is some sort of a region where that has some sort of width delta S. Let me clarify what I mean by delta S. Let's say what I mean by UV versus infrared is E to some S, right? To just say that, you know, like there's, for example, some scale here, some scale here. This is like just parameterization. And of course, in the case of holography, what you would say is that if you have an operator supported on A, as you go into the bulk, there are two stages to the renormalization of that operator. In the first stage, if the operator was supported, the support of the operator shrinks exponentially fast, as Brian taught us. So there's stage one, this is stage one. The support of the the support of the operator UV operators shrinks exponentially fast. Right? So if operator was supported on A, as I flow to some other scale, its support is shrinking. There is stage two. That's when the support of the operator has reached your cutoff. And then at that point, what happens is that past that point, the norm of the operator, of the operator shrinks, as we'll see. And over here, in holography, the second stage is invisible. The moment you reach a point, immediately, just if you move an epsilon away from this, there's no smooth transition region, right? You move a little bit outside, the norm of the operator has dropped to 0. And we'll see why that's the case. Because in RG flow, when you flow an operator supported on A past this point, the way it behaves is like this. So for example, let's say Y is a point here. The norm of the operator falls exponentially like e to minus delta S delta delta. So this delta S is the width of the region, and delta delta is the gap in the spectrum. When I say, so this is a heavy operator, right? This is a heavy operator. So what I mean by that is that, so this is a CFT. We grouped all the primaries, conformal primaries, into two groups. So these are conformal primaries. I'm going to call these guys light, and I'm going to call these guys heavy. And then there is some sort of a gap here. At this point, you don't need the gap to be large. If the gap is large, the norm falls very, very fast. You move out, this region is very, very narrow. But even if the gap is small, is order 1, by tuning this delta S to be very, very large, you still accomplish the same thing, right? So in holography, what happens is that there is a gap here that's order n squared. So the heavy operators, heavy stringy operators, will immediately, the moment you move outside of the RT surface, the norm immediately drops to 0. Sorry?
Sorry, when you say stringy, do you mean string states? Like, then the gap would be, why do you say n squared and not lambda to 1
sorry,
quarter?
I should clarify this. What I mean here, I'm just making, I shouldn't call it stringy, non-supergravity modes. So there's a mechanism for operators that are that come from dimension order 1, and then there are operators that are much heavier.
So, sorry, so your gap is what in that case? In the n equals 4, what would be your gap?
It's going to scale with n.
What about the stringy states that scale like lambda to 1 quarter?
Yeah, I guess those are also going to be large. Yeah, those are also going to be large. But the point is that there is always, I mean, you need a large gap to protect against whatever mode
Yeah, I understand. I just want to understand if this gap should scale like n or the Toft coupling or some other parameter. Because you said it's n squared, so I was wondering if that's important.
Yeah, I guess I talked a little bit. That was not very.
Okay.
Yeah, that was not a sharp statement.
Okay, thanks.
Yeah. So, but there's a large gap. There's a large gap. Yes.
Thanks. Sorry. Yeah, so I just wanted to clarify something about the gap as well. I'm going to, so this is the gap for what kind of operators?
So,
in other words, is it going to be,
Yeah.
is spin going to be important? Is the fact that a single tray is going to be important?
yeah, so let's say at this point what I'm talking about is a general CFD. And I arbitrarily split them into two groups, right? Light and heavy. And I just call something a gap in the conformal dimensions, right? That need not be large. The formalism of quantum error correction tells you that the light operators are in the infrared, or all the operators in the infrared are protected against the heavy operators in the UV by errors that scale like this. Now, if the gap is order 1, you just have to go really deep in the infrared to be protected. But if the gap is large for general CFD for whatever reason, I don't know if it's strongly coupled or something, without large n or with large n, then you have a sharp, you have very, very strong, well, you have almost exact quantum error correction that protects you against heavy operators in the UV, not light operators, right? So I'm just discussing this formalism. As I said, this is the only one that generalizes to an arbitrary RG flow. The second one is specific to large N theories. So I want to make this, the reason I'm trying to make this distinction is that the earlier papers on quantum error correction motivated quantum error correction in RG, in holography by saying the commutators between phi x and phi y, supergravity modes vanish, right? But then if you look at later papers by, for example, Harlow and other people that talked about derivation of the RT formula from quantum error correction, that really focuses on this part of the story. Okay, any other questions? Did I sort of address the question? Yeah. Yeah, I guess I talked loosely when I said order n squared. I just meant some large gap. So the lesson here is that you could talk about error correction, quantum error correction in a large N theory with small coupling, as we are studying in a large N O1 model, right? This is our upcoming paper, in which you are protected against light UV operators, but not against heavy UV operators. Or you could talk about quantum error correction in a large gap theory without large N, where it's reversed. The role is reversed. And by the way, I should have mentioned this. So well, actually, maybe I should say this. Of course, here, the mechanism for protection is that you have error correction if the commutators vanish. And the commutators of light operators vanish in large N because of large N factorization. Right? That's the mechanism for here. All right, any other questions? This was sort of the holography part that I never get to. Now we go back to a regular talk and discuss why is there quantum error correction in holography, in RG. Any questions? So hopefully the plan is clear. We are going to take a CFD or quantum field theory, group the operators into two groups, large and heavy, and we're going to argue that as we flow towards the infrared, as we consider the renormalization group flow of low operators, heavy operators, smooth that over some region A, there are two stages, as was first discussed in the case of Mira by Kim and Castoriano in 2017. There are two stages. In stage 1, the support of the operator shrinks exponentially fast. This is clear from Mira. But we're going to work this out, or if we have time, in C-Mira or using Polchinski's exact RG. And then in the second stage, what happens is that the norm of the operator, heavy operator, drops exponentially fast. All right, so now this is the summary of this part. I'm just going to go back and in the remaining, how much? Half hour, is that right? Okay, in the remaining half hour, I'll tell you why is there quantum error correction in RG. Please feel free to stop me at any point, because at some point the discussion might get a little bit formal. Or, yes?
Maybe, hello, can you hear me? Okay. Maybe this is naive, but is this obvious that this, because you explained that this OUV is very different for this different classes, like for this heavy and light modes and so on, but is it obvious that this W has no basically information about, I don't know, holographic person?
Okay, you're asking, is it obvious that RG could be modeled using an isometric map? Very good. So I have a slide or a discussion prepared for this at the very end of the talk. No, it's not obvious. It's one way of modeling RG. As a matter of fact, so RG flow could be modeled with Mira or CMira using an isometric map. There could be non-isometric maps, and in particular, this beautiful paper by Vidal and friends. I'm sorry that I don't remember the collaborators that argue about, how there are other RG flows that correspond to non-isometric maps. There's a null direct. Non-isometric RG flows could be maybe thought of as sort of like going radially in, and then Mira should be thought of as like going on a null direction inwards, or discussions of that type. But here, I will actually specifically focus on the mechanism that essentially relies on the fact that the map is an isometry. Now, what goes on with the non-isometric map is another beautiful story, but I won't have time to go over it. That's a very good question. I do have to say that the exact RG flow of Polchinski is an isometric map. This was something that surprised me, at least. That's sort of like what typical high-energy theorist considers to be like a very nice way of defining RG. All right, so a review of quantum error correction codes, quantum error correction in the Heisenberg picture, perhaps in a form that is hopefully a little bit simpler than what you've seen before, but it comes that no, I'm not making any compromises. I'm not oversimplifying. What's important is that I'm reviewing exact quantum error correction codes. So exact quantum error correction is significantly simpler. Could be explained in a much simpler way. Roughly speaking, the cartoon to have in mind is this. You have some Hilbert space HA and some Hilbert space HB. This is a cartoon. There is a divide between them. You encode your logical operators in HA. Oh, I'm sorry. And noise acts on HB, right? Because these are two different Hilbert spaces, A logical and O noise commute. And this is the essence of quantum error correction in the Heisenberg picture, as simple as this. So your code subspace in the Schrodinger picture, it's a concept that's in the Schrodinger picture, is basically, the code states are things that you get by acting with logical operators on some base state. And yeah, so this is the basic picture. Now, this looks completely trivial, but let me explain a little bit more. So let me give you 3 examples of realizing this cartoon. The first example is when HA is HA tensor HB. This is called the subsystem quantum error correction. The second example is when H is HA direct sum HB. This is called a subspace quantum error correction. And the most general case is the mixed quantum error correction. In finite quantum systems, there's no other way of realizing this divide. And that is when you have a bunch of sectors, so direct sum over tensor products. So you might tell me that this is completely trivial, and that you're absolutely right. But the magic of it, the magic of quantum error correction, is that this basis I'm drawing here is not a local basis. So if I have n cube, if I'm encoding 1 qubit in, I don't know, 5 qubits, for example, in a famous, using a particular code, there is a unitary that acts, a non-local unitary that acts on the 5 qubits that will bring you to this basis. This is 1 qubit where you've encoded your information, and this is where noise acts. But this unitary is where all the non-triviality of quantum error correction lies, right? So you take this picture, and you rotate it using some sort of arbitrary non-local unitary. These are all different types of quantum error correction codes you can get. Basically, that's what it is. So the magic is about this UAB. Another way of thinking about this, so when I draw this line, what do I mean formally? What I mean formally is a subalgebra. There is the set of physical operators, which is all of these guys, and you encode your information in a subalgebra. In finite dimension, a generic subalgebra always has this form. The Hilbert space factors, there's a theorem that says the Hilbert space factors is a direct sum of a bunch of tensor products, and this is a general structure for subalgebra. In quantum field theory, you don't have these factorizations, but it doesn't matter. You have a subalgebra where you encode your information, then your noise is whatever commutes with your subalgebra. There's a formal name for it. It's called a commutant. So if you hear that word, it's just, that's what we mean over there. All right, so this is a quick review of quantum error correction codes, exact quantum error correction codes. Are there any questions? So hopefully this is much simpler than other presentations you've seen. Now, maybe this presentation, this is like a very nice way of talking about quantum error correction, but it's not the most practical way, because what we're interested in is often, we're not given this basis. We're often talking about some sort of other basis, right? So what can we write in the other basis? We know that the main point is this. There's a set of operators that generate the subalgebra of logical operators, then the commutant, whatever commutes with it, is the noise. So how do we formalize this? Neil and Laflamme taught us a very simple way to think about this. So the quantum error correction condition, a la Neil Laflamme, is this. Let me just write it like this. I talked about a subspace, right? Oh, sorry. Let me just write it this way. So the code states, these are code states. Take two of these guys, psi I, psi j, and put some noise operator here. Neil and Laflamme tell you that you have an error correction code if this is proportional, oh my God, to delta ij. This is the error correction condition. I mean, it should be easy to see it from that, but it's just like a... What's neat about this condition? So if you want to make this an equality, you'll have to put some coefficient that depends on the noise. What's nice about this is that it generalizes, this condition generalizes nicely to approximate error correction, where this picture gets a little bit messy. And that is simply by saying that this is correct up to some epsilon. Xij depends on O as well. So this is some small parameter that controls how good is an approximate error correction code. Of course, you know, like there's this, when I talk about noise, I always have to normalize my operators, because if I multiply my noise operator by a large number, this is going to get out of control. So of course, I'm talking about operators of unit norm or something, right? That's why I kept writing this equation, right? I divide by O noise. So this condition is the same as this in the Heisenberg picture. Okay, are there any questions? I absolutely recommend looking at the paper of Kim and Castoriano from 2017, where at least it was a place that inspired me to do this work, because they took Mira as an RG flow and they just analyzed it as, you know, like analyze all of this in that particular case, and they saw this nice structure of phase 1, you know, like phase 2 where the support shrinks and then the norm drops and such. But now I'm going to describe that in full generality in a way that's just applies to any quantum error correction that's isometric, classical, quantum, or whatever. And hopefully it will actually become clear. Well, I don't know how comfortable how nice you will find the formalism. It gets a little bit mathematical, but it's not, these are not difficult concepts to discuss. All right, so here is the summary of what I'm going to say. Let me just describe it before saying it. Every time I have a quantum channel, right, I'm going to get an approximate quantum error correction code in a very, very simple way. So this is going to be the message I'm going to send across, right? So in the case of exact quantum error correction, I need a subalgebra. How do I identify a subalgebra using a quantum channel? The subalgebra is going to be the set of invariant operators of the quantum channel. In analogy with RG, this quantum channel is the renormalization channel. You take an operator in the UV and push it towards the infrared. This is a quantum channel. The invariant operators of this quantum channel are going to be protected in an exact way. All right. So now I'm going to argue for you that there exists a quantum error correction code. So as I explained, all I need for exact quantum error correction is just a subalgebra. There are various ways to, you know, define a subalgebra. One way is you define it using a channel. And again, every time I talk about quantum channels, the thing to keep in mind is that this is the renormalization channel. It's the thing that pushes the operators from the UV to the infrared. So just to make that a little bit more precise, there is a so-called Stein-Spring dilation. Stein-Spring dilation theorem. Stein-Spring dilation theorem that says any quantum channel phi of A could be written in the following form: pi of AW. These are the isometers I talked about. This is just a representation. If you don't want to be talking about finite, if you want to focus on finite dimensional quantum system, this is just A tensor some identity. This is just saying that quantum, any quantum channel is just some partial trace in some enlarged Hilbert space. You have your system, you bring in some environment, you apply a unitary that mixes everything, and then you partial trace. This is the most general quantum channel in finite dimensions. In infinite dimensions, which that is going to be important for us because we're talking quantum field theory, and if you care about those stuff, you write it this way. This is an isometry. This is some representation. This is a representation of the algebra. So the isometry is from some HIR to HUV, but you know, this is a general quantum channel, so it's from some Hilbert space to some other Hilbert space. So the example to have in mind, as I said, is RG. So this is the example to have in mind. this W, I'm drawing pictures as if it's holography, right? Is the thing that pushes you from some slice deeper in the bulk, some scale lambda prime, to some scale lambda, pushes you towards the boundary, right? The map is from the infrared to the UV. And in the Heisenberg picture, so this is the Schrodinger picture, this is Schrodinger. In the Heisenberg picture, this corresponds to pushing the operators up using a quantum channel. This quantum channel sends UV operators to the infrared, right? So I just want to think of this as a renormalization. All right. Any questions about why I'm talking about quantum channels all of a sudden? So RG gives you an example of a like RG modeled by isometries, as is done in exact RG flow of Polchinski or C-Mira or Mira, is an example of a quantum channel, and all I need to argue for quantum error correction, approximate quantum error correction, is quantum channels. I don't care about the rest. If you give me a quantum channel, I'll construct for you an approximate error correction code in a way that I'm going to tell you in a second. Any questions about this? I have to say, a lot of this was, as I said, was abstracted out of the work of Kim and Castoriano. So they played an important role in our understanding of it. So you give me a generic channel. Which is, by that, I mean, in case you guys are math-oriented, it's a unital CP map, a unital completely positive map. If it's generic, it means that it has no Jordan blocks. So if you do have Jordan blocks, you just throw in a small perturbation, they will go away. In case you were worried about that. If not, just don't worry about that. So there is, for every quantum channel that doesn't have Jordan blocks, or said differently, for any generic quantum channel, there's a notion of a spectrum. These are the eigen operators of the channel. The operators that under the action of the channel are just multiplied by number. So this number is a property of channels because it's a unital CP map. Every quantum channel tells you that, for every quantum channel, this number is just a complex number. So real of lambda is larger than 0. This is important. The norm of this complex number e to minus lambda has to be less than 1. It's just because of the fact that W is an isometry in that language. So the spectrum is like to this side. Lambda equals 0 corresponds to a set of invariant operators of the channel. They form a subalgebra. And, well, voila, if you have if you give me a quantum channel, I can project to the invariant subalgebra and I get an exact quantum error correction code, right? But in the case of CFDs, this is the RG flow map. This is a renormalization map or scaling operator. And these are the conformal primaries and these are the conformal dimensions. And the invariant subalgebra for generic CFD is basically corresponds to a set of operators that have 0 conformal dimension, and that's unique in identity. So for generic CFD, I'm not going to get anything interesting, an exact error correction in an interesting way. And this statement is a statement that the conformal dimensions, when lambdas are positive, conformal dimensions are positive. Yeah, so lambda is the conformal dimension and x lambda are the conformal primaries in the case of CFTs. But in a general quantum channel, these guys could be complex. All right, good. So given a general quantum channel, von Neumann taught us how to project to the invariant subspace. It's just a simple trick. You do this. You apply phi n times and then sum over these guys and divide by n and take the limit of n going to infinity. This is a projection to the invariant subspace. You can easily convince yourself this is true. To the invariant subalgebra. It has a name. It's called conditional expectation. Now, let me tell you a little bit about the physics of these eigenvalues. There are channels that are called primitive channels. These are channels when lambda is not imaginary. What is an imaginary lambda? An imaginary lambda on this line corresponds to recurrences. So if you had a model of RG that had imaginary lambda, there will be recurrences. And statements like C-theorems basically tell you that you shouldn't have any operators with those properties, right? So there's a name for quantum channels that don't have imaginary eigenvalues. They're called primitive channels. And interestingly, primitive channels have this property that if you want to project to the invariant subspace, you don't need to take this sum of 1 plus phi plus phi 2 plus phi 3. All you need is just take the limit of phi tensor n. This is phi n. Just apply the map many, many, many times. It's basically Riemann-Hilbert theorem. So how do you get a quantum error correction code? It's pretty simple. Let me draw it actually using the same picture I drew here so that you guys have RG flow in mind. I'm in the UV and I want to flow to the infrared. Let's say an infinitesimal RG step is phi. I'm just going to flow really deep in the infrared. I apply phi many, many, many times. As I flow deep in the infrared, this approximately projects to the invariant subspace, or said differently, it basically projects to, doesn't project. It suppresses, throws out operators that have large conformal dimensions. So the message that I'm going to go over in the remaining time is this. For a CFT, the spectrum, you could split it in an ad hoc way into heavy and light operators with some sort of a gap. Remember that these are conformal dimensions are the lambdas, right? And basically, the heavy operators, as you flow towards the infrared, deep in the infrared, these are heavy operators. They're basically suppressed by e to minus n, this gap. At least they're suppressed by that. Right? This n is the thing that I call delta S up there. Right? It tells you how much you flow in the infrared. This is the mechanism behind passive error correction in holography. So basically the picture becomes something like this. Let me draw it here. That there is some sort of a W this way and then phi running this way, phi tensor n or something. There's an operator that's supported on a region here. As you flow towards the infrared, the support of this operator shrinks until it reaches some sort of a, it's comparable to the cutoff. Past that point, if you go deeper by some delta S, the operator, the norm of it drops, therefore the commutator as well as the correlators will just go away. So there is some sort of a vague notion of smoothed out RT surface, if you wish, that becomes sharp in exact quantum error correction. So with that, I have to say, so this is the formalism I advocated. In the papers that I referenced at the beginning of the talk, what we did was that we basically, this formalism was applied to one-dimensional classical Ising model. You can see explicitly how this works. Then we applied this to C-Mira. The particular model that we looked at was Vidal and friends from 2018, which is super explicit. And we saw this structure over there as well. And now we're working in this structure out for a large NON model, but the punchline is that it goes through very, very nicely. So there are, I ran out of time. I don't have time to go over examples, but the structure was abstracted out of these explicit examples. All right, let me just summarize and stop. So in summary, hopefully, at least I'm gave you enough motivation to go look at those papers to see how a classical or quantum RG flow is an approximate classical or quantum error correction code. And then this is nice and pretty, but for this audience, or at least for me, the important thing was that this teaches us lessons in holography about the fact that first there are two types of different error correction codes in play, and one of them has to do with the large gap. This is passive quantum error correction, and the other one has to do with large N, which is active quantum error correction. Our paper about large N will come out soon, hopefully in a month or so, where you can see this distinction very clearly. We don't have a large gap, we just have large N. All right, thank you so much.
Thanks very much, Nima. Additional questions from the audience? I have one question, which is, I can see how you can get invariant subspace, but not algebra. Like, I interpreted that to mean if you apply the channel to like the product of two invariant operators, you were saying it's still invariant.
So, yeah, it's easy to prove this. It's a two-liner to prove that the set of invariant operators form a subalgebra. This is just a fact. So the way to use it, the way to prove this is you use the Schwarz inequality for quantum channels, and you show that it preserves multiplication. The catch is that it has to be a quantum channel, which is a unital CP map. Yeah. So if you use the non-isometric models, you lose this. Of course, if you have small fudge factors, then none of this works. Yeah.
Okay, thanks.
Sure.
Other questions?
One technical. So how do you define these norms of the operator in general? And does anything depend on these norms? Let's say like
how do I define the norms? Well, given are you worried about the fact that these operators are unbounded? Yeah. Well, okay. So in the finite quantum systems, of course, we're not worried about this. In quantum field theory, we're talking about the algebra of observables, which is the set of bounded operators. It's a one-Neumann algebra. So these guys are always. There are two ways to think about them. Either you can think about unitaries or spectral truncations of field operators. They're equivalent. This was like, yeah, they're basically similar in the spirit. I mean, you just take an operator, you take a spectrum, unbounded operator spectrum, and a bounded function of an unbounded operator is a bounded operator. So yeah.
So in this approximate error correction, you have this epsilon, and does this depend on the norm on the operator, or like?
Yeah. So I was careful to divide always by this norm, right? It's only fair to talk about this quantity, right? There exists no error correction code that is insensitive to this, right? This part in particular becomes very clear when you talk about harmonic oscillator quantum error correction codes, right? In the harmonic oscillator cases, which are studied by standard formalism, of course, you always have to talk about these. So one nice way to think about this stuff is that you can simply talk about the protection against the group of unitaries generated by the noise. If you provide protection against that, you're in good shape. This is usually the way it's formulated for harmonic oscillators.
All right, let's thank Nima again.